Hello. So we are going to review homework 2 today. So the midterm exam is on Wednesday. So I'd like to review your homework answers before the midterm exam. So I'm doing it quickly. Homework 2 is about endogeneity and instrumental variable method. And my focus was more on like examples, more naturally occurring like economic settings can imply endogeneity. So I want you to show you under like some examples of endogeneity, natural endogeneity. So first question is about measurement error. We assume simple Cobb-Douglas production function, and I showed you how we derive regression equation based on the Cobb-Douglas functional form. So it's straightforward, just taking log. And by the way, this kind of regression equation is actually used in macroeconomics. Maybe these days, maybe not, but like when I was a student, this kind of derivation was not rare, kind of common. And always, excuse me, in this case, the problem arises from the capital in this case, because capital is intangible. Usually we don't know how much capital we have and how much has been depreciated. So we cannot follow the depreciation like every year, and it is not observable. So we rely on some accounting methods. If you have taken some accounting classes, you know that there are different just formulas to calculate the depreciation of, say, a building or machinery. So it's just based on accounting, not exact measurement of how much capital, say, a factory has, a company has. And like, for example, capital includes something like brand power. Brand power is not measurable. There are ways to measure that, but almost always it is not perfect. So we have to think about measurement error in this example. And I think it's not, it is pretty straightforward in this example. Everything is so like answering the question was not a big problem. But what I want to tell you here is, like this example, this is the true model. I already gave you that the name of this equation is the true model, and this is the estimating model. So in this case, what we assume is this equation and this equation. So these two equations are what we believe the truth. But this equation is not certain. We are just estimating this because this is what we have, but we are not sure if this makes sense or if this is this satisfies the classical linear regression assumptions, blah blah blah. So in this kind of cases, like the fundamental structure of this model is again this and this, right? So alpha tilde, beta tilde is something that we do not know what it is. We hope beta tilde equals to beta 0. Gamma tilde equals to gamma 0. That is what we need to show. And the reason why I'm telling you this is because we are assuming these two equations. You have to express what you have to do here is you have to express this equation using the other two, right? Not the other way. So for example, I have seen some like I think most of you have done well. Okay, nice. You guys did well. So later, I think maybe this later, if the model becomes more complicated, you have to distinguish what is assumed and what is uncertain, what you are investigating. And here, another thing, it's my fault. I should have been more concrete. The misspecification bias here, I meant the difference between beta tilde and beta 0, right? So that's what I meant. So when you replace k with h, beta tilde may be different from the true value beta 0. That's what I meant by the misspecification bias. Most of you have done really well. And conjecture the sign of the bias. You can tell the sign is not, so telling the sign is obvious in this case because you can derive the sign of the, you can derive the covariance is negative. Because the covariance is negative, so you can easily tell the sign of the misspecification bias. So let me see. Any comments? So let me see. Did well. Good job. Nothing much to say. Okay. And then here in part D, this gives you the idea of instrument. In this case, measurement error, often it is assumed that there are different measures. There are multiple measures. Like in this case, I considered different accounting methods, like different formulas to calculate the depreciation, and like different measures of capital or something like that. I don't know. But then the other another proxy variable can serve as an instrument. So this is another variable that measures the capital with the different measurement error. But the measurement error is now statistically independent of the other measurement error. So there are two different measurement errors, but they are independent with each other. Then we can identify what is going on. Right? It's a very an interesting case. And then you have to show the validity here. And the point here is you need to show the relevance condition, and you need to show the independence assumption, relevance and independence. The idea is correct, but the problem here is you have three regressors: constant, L, labor, and capital. So there are three regressors, so it is not as simple as calculating covariance. So relevance condition is not just covariance different from 0. Intuition is not wrong, but what I wanted you to do is something like this. We have to consider the full rank assumption because there are three regressors, and you may delete the constant by taking demeaned variables. Demean all the variables, and simply I replace all the variables with variable tilde. Then it means the mean is 0, and z so this is the regressors, x is regressors, and z is exogenous variables. And then what we need to show for the identification is the exogeneity condition, which is pretty obvious, easy to verify. And also you need to show this. This is the relevance condition. Relevance condition is this, not simply covariance equals to covariance different from 0. And then it is 2 by 2 matrix. So to show that the 2 by 2 matrix is invariable, the determinant is non-zero, which can be written in this way. And now replace h and g with k plus something. So h and g becomes, so like h tilde, g tilde becomes k squared. K tilde squared because u and v are independent and mean 0. And, so h is replaced by k, g is replaced by k. The measurement error is vanished because its expectation is 0. And then in the end, this is the relevance condition. the relevance condition should be stated in this way. And what's interesting here is the relevance condition, the full rank condition, is on the true capital, not the measurement error. As long as the measurement error is statistically independent, what you need is the same full rank condition as if there was no measurement error in capital, right? So that's what I wanted to point out from this question. Like most of you, all of you did not consider the multiple variables. And in this case, I know you understand the problem, and but the problem is being rigorous. So you know the answer. So just stating the answer is not enough. Like, so I want you to practice how to write rigorously, how to write your argument mathematically. And in this case, if you do not want to make this derivation, or if you cannot do that, just mention that you know the problem, but like it's difficult or it's just too cumbersome, takes too much time. So I'm going to simplify the question like this. For example, if you have assumed labor is uncorrelated with capital, like actually K, it's not H, and then can be H, yeah. If they are uncorrelated, then easily you can ignore L by the theory of partition regression model. So that's another way you can handle that. So I know that you know the material. So answering the question is not a big problem, but I want you to practice writing. It's like learning a new language of econometrics. So you have to be more rigorous in your argument, right? And go back to the question. So this is that, and then finally, weak instrument. Weak instrument is also it's like let me just show you how we have done this. So you can do it as a fitted value approach. Using a fitted value approach, I regress the endogenous variable h on exogenous variable and instrumental variable. So this is the first stage equation of the fitted value approach. So you have to consider L tilde in here. I think all of you just ignored L at all. Just consider covariance between H and G. That is not rigorous enough. But I understand you know what's going on. So then in this case, as you know, the weak instrument happens if delta 2 converges to 0. If delta 2 is close to 0, then something is wrong, some problem arises. To derive that, delta 2 can be written as this, just derivation. By the way, the algebra may be wrong. I'm not certain if I'm correct, but it should be approximately correct. I think the answer is intuitively correct, so it should be correct. So anyhow, when you derive delta 2, you have to include L. L is included in there. So then delta 2 can be written this way explicitly. And it may look a little complicated, but so denominator and numerator has the same parts, and denominator has an additional term. So if the variance of the labor input is fixed, then it depends on the ratio between this guy and this guy. So this guy and this guy is basically what constitute the measure, the variable with measurement error. So look at this. it happens till the instrument becomes weak if the variance of the true capital is super smaller, much smaller than the variance of the measurement error, which is natural. So here you have a proxy h, but in this variation, in this proxy variable is mostly from the noise, the measurement error, then you have no information from this, right? That's when your instrument becomes weak. Your instrument gives you nothing. So that's what we can see from this one. Or like maybe this is also correlated to signal to noise ratio, which is important in information theory. The idea is simple. You have too much noise given your signal. Signal is the important part, but the noise is dominating the signal. Okay, that was part 1. I'm going to stop the video here, and we'll do question 2 in the next video. Thank you.